right, hello, welcome, and thank you very much for coming to our presentation to learn on hacking Binder. It's a big honor to be on the stage and present at OffensiveCon24. Here is a quick overview of our presentation. After a quick introduction in Android Binder, we will provide details of root cause of the vulnerability, which is underlying these two CVEs here, resulting in use after free issues in the Binder kernel module. Then we will dive into the exploitation of this vulnerability on Android devices to do privilege escalation and get root privileges. And then we will focus on how we found this vulnerability, what was our methodology. We developed a custom fuzzer for that, and we will finally conclude the talk with some tooling which we developed in this exercise. Before we start, a quick introduction on who we are. Both Gulshan, Z, and myself, we are part of Android Red Team at Google, where we do offensive security research targeting Android features, mostly focusing on Android platform, kernel, low-level firmware. Essentially, we do our exercise in the time-boxed engagements, opportunistically collaborating with the feature teams in the white box model, so that we go just simply beyond bug finding, developing fuzzing and static analysis to hand off this fuzzing to feature teams to have a long-lasting impact. We do challenge assumptions, we do find vulnerabilities, we also exploit these vulnerabilities to create a proof of concepts demonstrating a real end impact of the issues to the stakeholders, and to also assess the efficacy of the mitigations available on the platform and inform with any recommendations. Based on the previous introductions, I think people in this audience are pretty familiar what Android Binder is, but for those who are not, just a quick recap. Binder is a keystone component in Android, which provides an inter-process communication which essentially mediates and facilitates exchange of IPC messages across processes in Android, across Android Sandbox. It supports multiple features, peer-to-peer communication, passing file descriptors, complex data structures, including pointers, and so on and so forth. It basically provides a basis for implementing a remote RPC mechanism, which is used by the framework services written in Java and C++. And essentially consists of two parts: a user space library, which is known as libbinder or libhardwarebinder, and a corresponding kernel module, which is accessible at devbinder or dev hardware binder or VND binder. Specifically for this presentation, we will be focusing on kernel mode component, leaving the user space part outside of this presentation, although it's also very interesting. Why we decided to look at the binder? Well, there is a number of reasons for that. First of all, it is very interesting from the attacker point of view, because this is a key component of Android available on pretty much like all the Android devices. And if there is a vulnerability in this component, it affects a lot of devices, a lot of users. It is very universal in the sense. Another very compelling reason to look for bugs in binder is because it is available to your code running in the context of the unprivileged applications, which means like you don't need to have any special privileges. You just simply open devbinder and you can send ioctls. And moreover, this component is only one of few drivers which is accessible to the most heavily sandboxed processes in Android, such as, for instance, Chrome renderer process, which runs in the context of the isolated app as a Linux context. Although the set of the endpoints with which untrusted code running inside of the isolated app context can communicate is restricted. The previous history of the vulnerabilities is also very interesting. Like on this slide, we have some names of the vulnerabilities, and this list is not definitive, so please forgive me if we missed something. It is just big names which attracted a lot of attention and were discussed at conferences and media. So basically, almost every year we have an exploitable vulnerability in Binder, given that its size is relatively small, about 7,000 lines of code. But if we average the total number of vulnerabilities identified in this component, we will get a pretty high density, about 3 bugs per 1,000 lines of code. And looking at this trend, the situation is not improving. So we decided to look what's going on and why this trend continues. And in fact, despite the small size, a binder is highly complex It implements a very complex object lifetime management scheme. For instance, we counted about 6 different reference counters using to manage object lifetime. It implements a very highly complex multi-threading model because it's very critical for the performance of the Android, and even small regressions in the performance of binder can have a very significant effects on the user experience on the device. So there is five locks. The code is very dense, and Z and Gulshan and myself, we didn't have any prior experience with binders. So when we started looking at this code, briefly skimmed through it, we realized, oh, probably like data races are going to be the most common class of issues we should be focusing on. However, after doing some studying, especially previous research, and looking more at the code, we realized that actually the binder mostly suffers from use after free vulnerabilities, which has different root causes. For instance, it can be issues in the cleanup logic in the function. It can be misconfiguration of the reference counting and race conditions. And specifically for this presentation, we found an issue in the cleanup logic. Just a quick threat model, just to explain rules of the game. We assume that we have local code execution on a victim device. We're running in the context of the untrusted application. For the purpose of this research, we also assume that we control both ends of the IPC endpoints, because binders basically provides IPC interface, so there should be at least 2 entities which talk to each other over binder, and we assume that we as attackers both control sender and recipient, and we essentially use the interface exposed by the binder driver exposed over the IUCTLs to elevate privileges, either achieve kernel read-write or get root privileges. Now, before we go into the vulnerabilities, I would like to introduce some concepts which are essential for understanding the root cause of the vulnerability. And on this slide, we can see that there are two processes, process A and process B. And let's see what it takes from the point of the driver to establish communication between them. So process A implements my service, which, for instance, can be instantiated as an object which implements the service at certain address. And process A would like to expose this my service to process B so that process B can call RPC methods implemented in my interface, in my service. For that reason, process A sends a special IOCTL to forward information about my service to process B. When this happens, the binder driver will create a special data structure, which is called binder node. And node can be thought of as a wrapped pointer in the kernel, so basically complex data structure with multiple reference counters, but in this case, for the simplicity, we just show that there is one ref count here. And basically node represents an IPC endpoint. Next, driver also creates another object, which is called ref, binder ref, which refers to binder node 0xbeef created before. And we can see that we bumped up the reference counter to 1, because right now we have a reference object ref referring to binder node, and to prevent release in this memory, the ref count is incremented. And then binder notifies process B that there is a reference to binder node, and you can use this reference to communicate with the service to do RPC interfaces. So basically, right now, process B knows how to reach my service over binder. But the important takeaway here, there is object node, which is translated to object ref, and ref refers to node. You might ask a question, how does the binder figures out how to send node to process B? Because they might not have any information about each other a priori. And for that, there is a special notion of context manager. Essentially, context manager is a special binder IPC endpoint, always available at handle 0. It means like any process can open this IPC endpoint and send binder node to it. And in Android, there is a special process called service manager, which takes role of context manager in binder. And there can be only one context manager for dev/binder. And then the context manager is basically used as a central directory, which knows all the binder nodes for all the IPC nodes available in Android. And any service which would like to communicate to the services, they will reach out to the context manager and say, hey, can you give me please node for this service? And this is how the process A and process B will know each other. Another important data structure which is used in communication is transaction, binder transaction, because this is how the process exchange information with each other using transactions. There is a field called write size and write buffer, and there is also read fields, but we can ignore them for the sake of our discussion. And essentially, a binder transaction allows sender to send to recipient binder objects. And binder object can be a node, for instance, as we've seen previously. It can be reference, it can be a Linux file descriptor, or it can be like more complicated data structure, including some pointers. And these objects will be passed in write buffer, which is essentially laid out as binder transaction data. And if you look at this structure, we can see that there is a interesting field here. First of all, there is a buffer, which is basically buffer which lists binder objects which are being sent as part of this transaction. And there is another very important field called offsets. Offsets is an array of offsets at which binder objects are located in the transaction buffer. So we can see here that, for instance, at offset 0 we have one object, the next going is offset 8, and the first object is binder type binder. Essentially, binder type binder is a node, and the second object is a file descriptor, Linux file descriptor. And as these objects are being sent from the sender to the recipient, they need to be translated from the context of the sender in the context of the recipient. Because, for instance, if we take, for example, a file handle file descriptor, this file descriptor is valid in the context of the process A, but it doesn't make any sense in the context of the process B. So basically, there should be some translation happening. And this translation is very interesting and complicated logic implemented in binder, and this is where we found an issue, which I think we're ready to take a look at. So basically, there is a translation of objects in the binder transaction. And on this slide, we can see a snippet of the code from the function which handles the transaction. And there is a for loop which iterates through the objects in the binder transaction. So we can see that we start with buffer offset 0, which means like we start from the very beginning of the buffer, and then we handle one object sequentially. Obviously, there may be error during translations. And when an error is encountered, we're taking a special error handling function, which is called binder transaction buffer release, because transaction the transaction can only succeed or fail. It cannot be in the intermediate state. And essentially, if there are some objects which are successfully translated before the failure happens, their translation has side effects on the global state. For instance, it can result in incrementing or decrementing reference counters, creating file descriptors, and if the transaction fails, we need to roll back all those side effects on the global state. Basically, we need to untranslate all the objects which were successfully translated before the failure is detected. And the function binder transaction buffer release is actually responsible for that. It takes the following arguments, but the most interesting arguments are the last two, is failure, indicating that if the failure was encountered during translation and processing transaction, in this case, this is true. And second is the buffer offset. And this is the offset at which error actually happened, so that this function knows exactly how many objects it needs to undo, untranslate, to roll back all the side effects. And interestingly, there is also a path to take error handling path before we are hitting for loop on this slide. So we can see that, for instance, if there are some properties of transaction is incorrect, for instance, the offset size should be aligned to the value of 8. If the offset size is not aligned, we will be taking this error path before hitting the for loop. It means that we will be calling this function, binder transaction buffer release function, with the buffer offset equals to 0, because we didn't process anything. And let's take a look at this function. So essentially, the failed at argument of this function is the offset of the object which failed during translation, and this failure is true. And this function tries to calculate the offsets of the object which it should untranslate. And as you can see here, there is an interesting logic. So if failure is true and failed at is 0, well, we should immediately exit from this function because we didn't translate any objects. There is no objects to roll back their translation side effects. But in this case, the failed data is actually overloaded, and we believe this is probably the root cause of this problem. And if failure is true and failed at is 0, we're setting the end offset is end of the buffer. It means that if we hit this function without translating any objects, this function will untranslate all the objects in the buffer transaction. And for example, as we can see here, we can see that there is an untranslation code for binder type binder, which corresponds to a binder node. And we can see that it calls binder dec node function right here, which decrements a reference counter on the binder node without incrementing it previously. This introduces inconsistency in the reference counting implementation and can result in the use of the free vulnerability. And here is just a high-level overview of the flow, how the transaction is handled. We can see that at the very beginning, we start in the binder transaction. We copy all the transaction objects from the user space into the kernel buffer. This is actually also a very important block we'll speak about later. And then we validate transaction. If the transaction validation fails, for instance, we provided the unaligned offset size, we will take the vulnerable path. We will go straight to the untranslate stage, and we will untranslate objects in the binder buffer, and as a result, decrement reference counter, the object will be released, and we will hit use after free issue. Let's take a look how can we actually trigger this use after free issue. In this case, we're assuming that we have two processes, and those two processes will have thread A on the left side and thread B on the right side, and in the middle we have kernel memory corresponding to the binder. Thread A implements my service, 0xbeef, and there was some initial setup here. So we can see that there is binder node, 0xbeef, with reference count 2. Reference count 2 corresponds to, first, there is a ref object for thread B. This is one ref count, and the second ref count is corresponding to a pending transaction. So basically, thread B sent a transaction to thread A, but thread A didn't read this transaction. So basically, it's still pending in the queue on the side of the thread A. And that's how we get ref count 2 here. In the normal workflow, let's assume that thread B wants to send another transaction with object of type ref. In this case, binder will translate ref to node, and it will increment reference counter by 1. So now we can see that ref count is 3. Now let's take a look what happens if we are sending not a ref, but node, and with misaligned offset size. In this case, the transaction will not be processed correctly. The translation will not happen because the offset size is misaligned. We will take error path. However, we will start untranslating objects in this case. And this will result in decrement in reference counter. So right now we have ref count 1. What happens next? Next, we kill thread B. And essentially, this will drop ref count to 0 because object ref will be released. And right now, ref count is 0. The kernel thinks that, well, this object is no longer used. Let's free the memory. So we have freed memory, and we have a dangling pointer to this memory from the transaction, which is pending. And now the thread A can read this transaction using one of the ioctls, binder read-write ioctl, and this results in the use of the free vulnerability. So this is a very nice and convenient primitive when we control both ends of the endpoints, because we control precisely when the object is allocated, we control precisely when the object is freed, and on the thread A, we control when the object is used. So this is a very nice primitive to work with. A quick words on the remediation side. Essentially, as Z will explain in details, we identified this vulnerability via fuzzing. And we had a test case which reliably reproduced this vulnerability on the vulnerable kernels, which is 5.10 and 5.4 Android common kernels. When we tried this test case on 5.15, it didn't work. After understanding why, we realized that there is a patch which makes this test case non-reproducible. Essentially, before this patch, the copy operation of all the binder objects from user buffer into the binder kernel buffer was happening at the very beginning of the function. So basically, all these objects were copied in the binder kernel buffer before we hit before we hit error handling path. And when we go to the error handling path, we start untranslate objects in this kernel buffer, and we hit use after free. This patch actually moved this copy operation from the very beginning of the function in the for loop itself. So basically, objects started to be copied into the kernel buffer as they are being processed. And if we take a vulnerable path in the very beginning, the binder kernel buffer is empty. And essentially, we have no objects to untranslate, and the use after free issue is not triggerable. And this CVE was fixed by backporting this patch to the vulnerable kernels. And on this slide, we can see what actually happened. So we can see that this block, copy all transaction objects from user space into kernel buffer, was moved here inside the loop. And if we take this error path here from validate transaction, we will go to your untranslate stage, and the kernel buffer is empty, and as a result, the issue is not reproducible. However, the binder kernel buffer is not zeroed between ioctals. And it means that if previously there was a successfully processed transactions, there will be objects from this transaction remaining in the kernel buffer. And when we hit our error path using second transaction, the binder transaction buffer release will process those objects and essentially hit use after free issue. And well, our fuzzer was smarter than us. It figured out this before we realized there is a problem. So shortly after the issue was patched in our test case, the fuzzer came up with another test case which takes one more step. So basically the fuzzer sends first a legitimate, a valid transaction with the binder node, and this basically binder node pollutes the kernel buffer. And then we do the same operation with this vulnerable malformed transaction buffer, transaction, and hit the binder transaction buffer release. And this issue was fixed completely and properly in the different CVE. And with that, I'm handing it off to Z for exploitation and fuzzing.
Thank you very much, Eugene. Let's dive into the exploit steps. There are 4 steps in our exploit. First, we exploit the vulnerability that Eugene just discussed to create a dangling pointer to a free binder node. Then we allocate a kernel object which overlays the free binder node so that we can exploit a use after free read to leak values from the kernel objects. Then we exploit the same vulnerability again, but this time we allocate a fake binder node with heap spray so we can exploit another unlinked primitive here. Using the leak primitive, we can leak a pointer to a struct file and override its inode pointer so that we can achieve an arbitrary read and bypass KSLR. Thanks to brute force security, these exploit steps are based on one of their exploit for CVE 2020-0041 in binder kernel driver. With those primitives in place, we can easily locate the task struct and CRED structures of our process, override its ID with 0, and disable as Linux. Let's dive into each step in detail. When reading a transaction, binder calls the binder thread read functions. The binder thread read functions copies two fields from a binder node, which are pointer at offset 88 and cookie at offset 96 into a binder transaction data. Then it copies this binder transaction data back to the user space. So we can exploit this use after free read to leak 2 8 bytes values back to the user space. However, how do we make this more useful? So we want to leak values from other kernel objects. After freeing the binder node, we can allocate another kernel object from the same memory location where the binder node was. For example, here we allocate an EP item object. Then using the same the leak primitive we just discussed, we can leak the pointer values in next and pref fields of the EP item object back to the user space. We will explain why we choose this EP item object. At this point, we want to figure out how we can get some kernel objects to overlay our free binder node. As we mentioned, we will be getting a struct EP item onto our free binder node. If you think about use after free bugs in user space application using the standard glibc allocator on Linux, getting some objects allocated to be allocated at the free binder node, free objects location isn't difficult because all objects of the same size are allocated from the same free list regardless of their object types. However, the kernel is much more complicated because it has the concept of slab and caches. In particular, most caches only can contain one type of objects. So if the objects we want to get allocated here, which is the EP item, uses a different cache than the one binder node uses, then it's almost impossible to allocate an EP item from the same memory location where the free binder node was. There's also a number of mitigation that has been enabled in the Android Common kernel for the past few years. I wouldn't cover all of them, but I will mention cache aliasing. Without it, it makes exploiting a use after free bug much harder. Earlier, I mentioned that most caches can only hold one type of object, but with cache aliasing, if two objects hold same type, if two caches hold objects of the same size, the kernel would combine them into one cache as an optimization. This is great for us attackers exploiting a use after free bug. And in fact, this was used in the past binder exploit. But however, cache aliasing isn't available for the EP item cache because there's a flag added in the kernel code, which is the slab account flag, which makes our exploitation much harder. If the objects we are exploiting are allocated from different caches, what can we do to overlap them? We will use a technique that's now commonly known as cross-cache attack. But first, we will examine how memory allocation works in the kernel. When we are allocating objects, the first thing we need is a page from the physical memory to store that data. The page allocator, also known as the body allocator, is the component that does that. We don't need to know too much detail about the page allocator for this exploit, mainly because as an optimization, we can assume that there's a cache where all our allocated page will come from and all our free page will go back to. This cache essentially works like a stack. It's last in, first out. If a page is free, it goes back to the top of the page cache. And the next time, if a page is needed, it will get the page that was last free from the top of the cache. This performance optimization makes exploitation much easier because it's much more predictable. Now that we can allocate some pages, the next thing happens is that the slab allocator will grab those pages and use them as slabs. Here you can see that there are two caches. First, the kmalloc128 cache containing all objects of the size 128 bytes allocated with the kmalloc function. This is the cache where our binder node will be allocated from. And then event pool EPI cache, this is the cache where the EP item objects will be allocated from. As you can see that both objects are allocated from two completely different pages. But also notice that the place where those pages come from, the page allocators per CPU page cache, is shared among all slab caches. This means that if we can get a page containing our dangling node back to the page allocator and reallocate that page back to the event pool EPI cache, then we can allocate a EP item objects from the same memory location where our free binder node was. So how does this look in practice? So first, we will allocate a binder node. The allocation will come from the active slabs from the kmalloc 128 cache. The active slab is the current slab in use, while the partial slabs are only used when the active slab is full. Then we can exploit the vulnerability we just discussed to convert this binder node into a dangling node. Right now, our goal is to get this slab back to the page allocator. This means that we want to free all other objects in the slab. We can exploit the same vulnerability again and again to convert all the objects in the slab into a dangling node. However, the slab allocator doesn't just immediately return the page back to the page allocator. Only when a certain number of empty partial slabs grow to a certain number, then some of the slab allocator will free some of those partial slabs back to the page allocator. Now all the pages that containing our dangling nodes are in the per CPU page cache. Now we can just immediately allocate a bunch of EP items so that the event pool API cache will grab those pages from the page allocator. Then eventually one of the EP items will be allocated from where our free binder node was. Let's look under the hood on how these cross cache attacks work. So on the left, we have a Linux instance running on QEMU, and on the right, we have our debugger attached to the kernel. So first, our exploit allocates 1600 of binder nodes, and then now we break into the kernel to inspect the kmalloc 188 cache where our binder node is allocated from. Here you can see that there are active slabs and partial slabs, and then because we just allocated 1600 of nodes, most of the partial slabs here are almost full. Then we can inspect also our event pool API cache. Here you can see that there's no active slab or partial slabs in the event pool API cache. Now we will continue our exploit to free all those binder nodes we just allocated and allocate some EP item objects. And then we break into our debugger again to inspect the kmalloc 188 cache. Here we can see that there are a lot more empty partial slab with 0 item allocated. Scrolling up, you can see the number of the partial slabs that's in the kmalloc 188 cache. As you can see that the number is much more larger than what we have previously. Then we inspect our event pool API cache. As you can see that right now there's an active slab in the event pool API cache with 24 objects allocated. So at this point, we have successfully done cross-cache attack. We have allocated an event pool EP item from the same memory location where our binder node was. Then we will link a pointer to a struct file, which we will discuss next in the slide. Now that we know how to get an EP item allocated on the free binder node, let's explain why we choose that item. Here we can see again the fields, next, and pref, which are the kernel pointers we can link using the link primitive. These pointers are actually part of a linked list of EP items where the head of the linked list is in the struct file. This means that when we allocate some EP items and link those pointers, eventually one of them will point to a struct file. So how is that useful to us? We can turn it into an arbitrary read, but first we have to look in the kernel code to find what system calls is doing some operation on the struct file. For kernel exploitation, we are interested in functions that can get us to put user or copy to user because they return values back to the user space. We learned that there's an ioctor called file get block size. So what it does is that it gets the inode from the struct file, do some pointer operations, and copy the x_block size field back to the user space. In the put user function call, the first argument is the value that it copies to the user space. If we can control what it reads, we necessarily have an arbitrary read. Remember the inode here used in the first arguments comes from a struct file. This is the struct file that we previously located using the link primitive. Knowing both the address of the struct file and the offset of the inode, we can locate the inode location in the kernel memory address. Assume that we can modify the inode value here. We could point it to anywhere we want, but the easiest thing is to point it to an EP item object. The reason is that we already know the address of an EP item object from the previous step, and we can control the event.data field here with another syscall. So we can easily overlap that with the i_sp field of the inode. Then we can call the system call to modify the event.data here to point it to anywhere in the kernel address space, then call the file get block size ioctor. So then we have an arbitrary read. That's great, but we still need a way to modify the inode values here. So we will discuss about the unlinked primitive. First, we exploit the same vulnerability again, But this time, instead of allocate an EP item objects, we do a heap spray to allocate a bunch of fake binder node using the send message system call. We won't dive into details of the send message heap spray because it's a well-documented technique used in kernel exploitation. But the main point here is that with the heap spray, we can control nearly every field in the fake binder node. So we can trigger another use after free in the next slide. In the binder will call the binder dec node and ilog functions to decrement a ref count in the binder node. When the ref count reaches 0 and all other conditions are met, which are commented out here, the functions will remove the binder node from a linked list. This is why the send message heap spray is very important, because to pass all the checks here, we want to control all the fields to pass all the checks here, we want to control all the fields in the binder node. Once we reach this function, this will trigger a use after free unlink operation. Unlinking a node from a linked list is a common technique used in arbitrary write. If you are not familiar with the technique, it's summarized here in the equations here. This basically provides us a way to write what and where by controlling both the next and pref field. With those primitives in place, we can work our way to root. With the leak primitive and arbitrary read, we can easily locate the task struct and CRED structures of our process. Then, using the unlink primitive, we can override all the IDs with 0. And also, to disable SLE-nux, we can just override the SLE-nux state global variables, or especially its enforcing field to 0. At this stage, we basically achieve a root privilege and disable SLE-nux. We didn't continue to disable seccomp or enable all Linux capabilities, but however, these steps actually require more patching in the kernel. So we will demonstrate our demo on getting root on Pixel 6 and Pixel 7 devices. For convenience, we only targeted the Pixel devices, although the same vulnerability exists in other kernel and devices running the vulnerable kernel. On the left, we have the terminal showing the output of our exploit, and on the right, we have the screen capture of the Pixel 6 and Pixel 7 devices. First, we are going to show our devices are running on the vulnerable security patch level, January 2023. Then we start our malicious app and launch our exploit, which pops a root shell at port 1234. Since we already set up ADB to forward our TCP connection, we can just netcat into those root shell. So we will print the user ID to show that we have achieved root user and also disable SLE-nux by the permissive permission here. So right now, we basically successfully achieved root privilege on both Pixel 6 and Pixel 7 devices. Moving on, we will talk about how we discover this vulnerability by fuzzing binder with Linux kernel library. We started by looking at existing fuzzing effort using syscaller. Syscaller, which is a state-of-the-art kernel fuzzer, has been fuzzing binder for years. How it does that is that it generates program based on a list of syscall descriptions and execute them on the target machine. In the past, it managed to discover a vulnerability that was used in one of the previous exploits. But when looking at the line coverage, it only able to achieve about 25% of the code coverage. Since then, many new binder vulnerabilities were reported by other researchers every year. Therefore, we begin examining some challenges in binder fuzzing. First, binder interface involves complex data dependency. Unlike a parser, binder is an IPC driver that maintains complex states and requires multiple processes to coordinate with each other. Finally, its highly concurrent nature makes it hard to catch any race conditions issue. or reproduce any. We'll dive into each challenge briefly. A binder ioctl call is complicated and can consist of multiple data structures with buffer dependent on each other. For example, binder supports passing complex data structures with pointer inside them using the scatter-getter method. The users will pass their data and a binder buffer object for every object and pointer to define its layout. Binder is also a complex state machine with strict rules for synchronous IPC. For example, a binder client cannot send transaction to itself or have multiple outstanding transactions at a time. Therefore, it's hard to cover all binder functionalities with a single client that interacts with binder alone. Some inputs for the ioctl call depends on previous ioctl calls. For example, releasing a buffer requires passing the exact buffer location in the memory map, binder memory map, based on a previous binder ioctl call. These locations are controlled by binder internally, so we cannot determine them upfront based on our fast data. We need some logic to capture this information in the fuzzer to test those functions. Also, binder requires multiple processes to work together. All communication requires a client that acts as the context manager. If a new client wants to connect with another client, this is discussed by Eugene previously about the context manager. It must first send a node to the context manager, which then sends a corresponding ref to another client. So establishing a connection between two clients alone requires 3 processes or clients to work together. Before we talk about how we overcome those challenges in fuzzing, we will first introduce Linux kernel library, or LKL. Basically, LKL builds Linux kernel as a user space library. It's implemented as a custom Linux architecture port. However, you might ask, how is it different from user mode Linux or UML? LKL operates within the same process space as the user space application. Meanwhile, UML runs the kernel and user space application in separate processes with isolated address space. Then UML captures the system calls that happens in the user space application using ptrace and forward them to the kernel process to be handled. This separation of address space in UML poses a unique challenge for fuzzing. To retrieve code coverage from the UML kernel, we will need to integrate kcoff with a fuzzing engine in a separate process. But for LKL, we can simply instrument the kernel with standard code coverage and link it with a fuzz engine. This is the primary reason that attracted us to use LKL for fuzzing. There are 3 building blocks in LKL. Starting from the bottom, we have the host environment API, which abstracts away the host system resources, such as CPU threads and memory allocations. In the middle, we have the normal Linux kernel code. Above it is the LKL syscall API that's exposed to the user space application. So a user space applications interacts with the LKL syscall API as if they are making real system call on a Linux kernel. This allows us to easily execute kernel code in the user space without launching any VM, which gives us a way to easily perform kernel unit testing and, most importantly, fuzzing. We can leverage LKL to fuzz Linux kernel code in user space. To develop a fuzzer, we link our fuzzer harness with an in-process fuzzing engine such as libfuzzer and LKL. Then we instrument LKL with standard code coverage pass and enable kernel address sanitizer or KSAN to catch any memory corruptions issues. This approach offers us several advantages. By fuzzing the kernel in the user space on an x86 machine, we are able to achieve high performance. We also gain the flexibility to make custom kernel modifications, such as mocking out hardware or implementing a custom scheduler, which we will discuss more later. However, LKL comes with some limitations. Currently, it doesn't support symmetric multiprocessing. This means that the kernel runs on a single thread, This also prevents us from detecting certain types of race condition involving spin locks, because spin locks are replaced with no-op in non-SMP build. However, mutexes and wait for event functionality are not affected, as they still yield to other threads. Another limitation is that LKL is built exclusively for x86, which may lead to false positive or false negative in our findings. In other words, issues found on x86 might not be reproducible on ARM64 architecture, or issues that exist on ARM64 architecture might not be found on x86. We will walk through a short snippet of code to demonstrate how we interact with LKL from our C program. First, we initialize and boot the kernel by calling the LKL start kernel function, passing the kernel parameter. Then we can mount essential file system. This includes sysfs, proc, and dev file system where our binder driver will be located at. With the binder driver loaded, we can open a file descriptor and create a memory map for it. This is where we call the LKL syscall API. Notice how similar these functions call are to the standard Linux system call. For example, the LKL sysopen function call here is equivalent to the open system call from the host kernel. Finally, we can execute any ioctl operation on the binder device. Here we call the binder version ioctl. LKL provides a convenient syscall API that closely resembles the standard Linux system call. Let's continue to talk about how we overcome those challenges. We developed a fuzzing harness that simulates IPC interactions between multiple clients on binder. The fuzzer initializes 3 clients and one of them to be the context manager. Our fuzz data then determines the sequence of ioctl calls from every client. To illustrate this process, on the right we have a simplified text representation of a test case. This test case instructs the first client to write a transaction command, sending a binder object with the ID beef, the second client to perform a read and write command to release a buffer, and so on. Based on this structure, our fuzzer mutates and executes the sequence of ioctl calls, simulating a variety of binder IPC interactions. The last challenge is to cache any race conditions in LKL. As we mentioned, spin locks are replaced with no-op in LKL because it's built without SMP support. Also, some past vulnerabilities we have seen occur within a tiny race window. So we developed a randomized scheduler that uses fast data to decide the thread scheduling order. This is based on the concurrence project developed by Ned from Google Project Zero. Then we implement custom system calls to yield to the scheduler and insert them around interesting synchronization primitives such as spin locks and mutexes. So when the thread reaches these yield points, it passes control over to the randomized scheduler and decide which thread to schedule next. This approach enables the fuzzer to simulate various thread execution orders and even catch bugs that happens within a tiny race window. Also, because the scheduler relies on the fast data set, we can always reproduce the same thread execution orders and reliably produce a bug involving race conditions. Here's the result of our fuzzer. We are able to achieve 68% of line coverage, which is a significant increase compared to the existing fuzzing approach. With the fuzzer, we also discover the 2 CVEs that we just discussed. We are still running the fuzzer continuously on our internal cluster fuzz infra to find any new vulnerabilities in binder. There are some potential future works we are looking into. We plan to upstream our binder fuzzer to the LKL project so it can be accessible to anyone. Currently, the fuzz engine does not take into account of the thread interleaving information. We think about explore ways to include those information into the fuzzing engine, the fuzzer mutation engine, to enable the fuzzer to find different thread execution orders and potentially any new bugs. We could also address those challenges that we just did study in C-Scholar to improve its code coverage on Binder. While developing the exploit, we also created some tools that helped us. So first is the Linux exploit dev environment. This project quickly helps us to quickly set up a Linux or Android common kernel environment for exploit development. It runs the kernel in QEMU and supports both x86 and ARM64 architectures. We also contributed a few new plugins to the Pun debug projects, especially plugins to inspect the slab allocator, per CPU page cache, and binder. We also come up with a few simple BPF trace scripts to trace the slab and page allocations for the heap grooming and cross-cache attacks. Keep an eye on our GitHub project account for any future release of those tools. And that's it. Finally, thanks everyone for listening to our talk. Yeah, we are happy to answer any questions.
If there are no questions available, thank you very much again. We're here